Hello everyone. Let's continue with Chapter 6, Data Mining Algorithms. Let's discuss Bayesian classifiers. Probability reasoning and inferencing is really trying to use some approaches to think about assumptions that decision variables obey certain probability distributions, and data are drawn from that specific probability distributions. Let's first take a look at naive Bayesian classifier. The Bayesian classifier is to estimate the probability of all alternative models or hypotheses given data as evidence. In other words, what we were trying to get is what's on the right-hand side in this equation. That's a probability of hypothesis given the data as evidence. That's our target. And then this is called posterior probability. It is a hypothesis or model given the samples or training data set of S. So that's the probability of hypothesis given the training or sample data set. And then what we have on the right hand side is probability of the data set given hypothesis is called the likelihood of a probability of the data samples given the hypothesis is true. Hypothesis is the probability distribution, or specifically in the classification framework, it would be the classification probabilities or distributions. And then pH is something called prior probability of the hypothesis. Prior probability, prior knowledge, something that you already know about the hypothesis. And then this is something somehow incorporates any background knowledge about H. If no prior knowledge about a hypothesis, what you can do is you can leverage uniform distribution, use uniform distribution as a prior. So now if you look at the whole equation as a whole, you can see that probability of a hypothesis given the data can be estimated by probability of the data given the hypothesis times probability of the hypothesis divided by probability of sample. Majority of the time, what we do is we think that probability of hypothesis and probability of sample is going to both of those two numbers would be constant. So in other words, what we're trying to do is we're trying to seek a maximum posterior of probability of H given S. Because for PS, majority of the time is constant, so that's why we see that either we can maximize probability of H given S or maximize probability of S given H times pH. It's something called maximum likelihood. We're trying to maximize probability of S given H, which is a maximum likelihood. So when pH and PS are constant, maximum likelihood, maximum PS given H is equivalent to maximum of this, which is called maximum of posterior. So let's use a specific classification example. Let's say that we have a k different attribute values. In other words, k different independent variables, x1 all the way to xk, and its model function, the model hypothesis y equal to fx, forms a set of finite discrete values yi belongs to omega. So aim of Bayesian classifier is to estimate the probability of y given data. So instead of estimate probability of y given the data of x, what we can do is we can assign the class maximum probability based on max of the p y given xi, and yi is omega, which is equivalent to what we just discussed just now. Equivalent to because instead of estimating y probability of yi given the data, we can leverage Bayesian probability equation. We can use probability of the observation given yi times probability of yj, in this case yj, divided by probability of x1, the data being observed, which is essentially the same. This is our ps, this is our ph, this is our ps given h, to estimate ph given s. Now, because this probability that we are trying to get is sometimes very difficult to calculate, that's how we introduce this naive Bayesian. So a naive assumption is that all the data sample values are conditionally independent from each other, so that the joint probability, this joint probability can be estimated by a product of individual probability. So instead of estimating this joint probability, we can estimate the individual probability, and because we have this conditionally independent assumption, we can use multiplication of each individual probability together. Then this is a multiplication of k elements of that individual probability. Now, if we're trying to use our MAP maximum of posterior criteria to estimate that probability, then essentially we're trying to maximize the pyj times this multiplication component. Now, what we're trying to estimate is a maximization problem, and then a classifier that is trying to assign probabilities becomes a naive Bayesian classifier. This is naive Bayesian classifier, which is apparently based on this naive assumption that all the data sample values are conditionally independent from each other. Bayesian network. Bayesian network is also called Bayesnet or belief network. It's a probabilistic graphical model for representing knowledge about an uncertain domain when each node corresponds to a random variable and each edge represents a conditional probability for the corresponding random variable. Typically, a Bayesian network can be represented as directed acyclic graph. So if you studied graph theory, now you probably are aware DAG, directed acyclic graph, is one special type of graph. What it is it is directed. As you can see here, there is a direction from one node to the other. This is called directed graph. Acyclic, it doesn't have any cycles in the graph. It will not go back from no pain to 40 fan, no spin to 40 fan in this example. So there is no cycle, acyclic. So here it also says DAG without loop, acyclic graph already without loop. There is no self connection. There is no edge that does this. There's no edge that does this. It doesn't exist. Now, let's look at this example, right? So again, the node is, you should be aware that the node is a random variable, and the edge represents a conditional probability. So let's think about this example, right? The fan does not spin. The fan has a specific probability that it doesn't spin. And what is causing the fan? What is causing the fan not spin? It could be a faulty fan has issues, or could be the plug has problems for the plug. Or you know that if there's a faulty plug, then your charger would not work. So that's the Bayesian network. Of course, it can be more complicated, but at least here it's a simple Bayesian, simple Bayesian, sample Bayesian network, which is rather simple. Okay. Bayesian belief network uses a set of conditional independent probabilities, but not imposing all variable values. In other words, it uses nodes to represent variables and use arcs represent causality relationships in terms of conditional probabilities. However, it has two types of nodes. One type is called observable variables, and the other one is called observable. For the unobservable variables, we usually call it as hidden or latent variables as well. So just at high level, you should understand that the Bayesian belief networks have two types of variables. One type is called observable random variable. The other type is called hidden variable. In this example, you can see that we use X to be the observable random variable, and we use Z to be the hidden random variable. And the likelihood function of probability of sample given the hypothesis is a function of X and Z, and then we call it LXZ. The maximization of this likelihood function is to maximize the expectation of logarithm likelihood. It's very difficult to write explicitly, but you should remember that this Bayesian networks leverages something called expectation maximization method with the expectation step and the maximization step. And then expectation step is trying to define a quantity that is the expectation of the log likelihood, which starts with arbitrary values initially and repeated estimate their expectation. And then the aim of the M step is to use an optimizer to solve an optimization problem that's maximize QL and of this expectation. So now, Bayesian networks, Bayesian belief networks can be solved by expectation maximization algorithm. That's all of the discussion for Bayesian networks and Bayesian classifiers. I'll stop here and I'll see you. Thank you.